Welcome to this lesson on the allotropes of carbon. Today, we will explore how one single element, carbon, can take on so many different forms, from the sparkle of a diamond to the dark flakes of graphite, the soccer ball-shaped fullerenes, and the revolutionary single-atom-thick wonder material, graphene. Carbon is truly the element of infinite forms. Let us begin our journey into the molecular world of carbon allotropes. What exactly is allotropy? It comes from the Greek words meaning other way or other form. Allotropy is the property of an element to exist in two or more different physical forms while remaining the same element. Carbon is the champion of allotropic elements with over 10 known forms. The reason carbon can do this lies in its ability to hybridize its orbitals in different ways. sp3 for diamond, sp2 for graphite and graphene, and mixed forms for fullerenes. Even though the atoms are identical, the way they are arranged in space creates materials with wildly different properties. Let us now explore diamond. Diamond is the hardest known natural substance on Earth. Each carbon atom in diamond is bonded to 4 other carbon atoms using sp3 hybrid orbitals, forming a perfect three-dimensional tetrahedral network. These bonds are all sigma bonds, very strong and directional. The crystal structure is called diamond cubic. The bond angles are exactly 109.5 degrees, with bond lengths of 154 picometers. Because all 4 valence electrons are locked into covalent bonds, diamond does not conduct electricity. It is, however, an exceptional thermal conductor, 5 times better than copper. Beyond jewelry, diamond has remarkable industrial applications. Its hardness makes it essential for cutting, drilling, and polishing tools. Diamond-tipped saw blades and drill bits are used throughout construction and manufacturing. In research, diamond anvil cells can generate pressures exceeding 600 gigapascals. Diamond's thermal conductivity makes it ideal for heat sinks in high-power electronics. Most diamonds mined, about 80%, are industrial grade and used for abrasives. Synthetic diamonds are produced through high-pressure, high-temperature methods and chemical vapor deposition, with annual production reaching 400 million carats. Now we turn to graphite, the most stable form of carbon under normal conditions. Graphite has a completely different structure from diamond. Carbon atoms in graphite are sp2 hybridized, forming 3 sigma bonds at 120-degree angles within a plane, creating a honeycomb or hexagonal lattice. The bond length is 141.5 picometers. The 4th electron of each carbon occupies a p orbital that overlaps to form a delocalized pi electron system. These pi electrons are free to move, making graphite an electrical conductor along the planes. The layers are held together by weak van der Waals forces, allowing them to slide past each other easily. Graphite's unique properties make it incredibly useful. The most familiar application is in pencils, where graphite mixed with clay creates the writing core. As a dry lubricant, graphite works well in locks and bearings. In nuclear reactors, graphite serves as a neutron moderator. Carbon fiber, made from pyrolytic graphite, is exceptionally strong and lightweight for aerospace and sports equipment. Graphite crucibles withstand temperatures up to 3,000 degrees Celsius. Expandable graphite is used in fire seals. Graphite is the starting material for producing graphene. Fullerenes were discovered in 1985 by Harold Kroto, Robert Curl, and Richard Smalley, earning them the Nobel Prize in Chemistry in 1996. Fullerenes are hollow, closed-cage molecules made entirely of carbon atoms. The most famous is C60, buckminsterfullerene, which has 60 carbon atoms arranged in 12 pentagons and 20 hexagons, like a soccer ball. The molecule has a diameter of about 710 picometers. Each carbon is nearly sp2 hybridized, but the curvature introduces some sp3 character. Unlike diamond and graphite, fullerenes are soluble in organic solvents like toluene, forming beautiful purple solutions. Fullerenes have remarkable properties. When doped with alkali metals, solid fullerenes become superconductors, with transition temperatures up to 38 Kelvin. Fullerenes are excellent electron acceptors, accepting up to 6 electrons reversibly, making them valuable for organic solar cells. In medicine, fullerenes are investigated for drug delivery, as antioxidants, and for photodynamic therapy. Carbon nanotubes, discovered in 1991, are graphene sheets rolled into seamless cylinders. They are single-walled or multi-walled, with nanometer diameters. Nanotubes are about 100 times stronger than steel, at 1/6 the weight. Graphene is perhaps the most exciting carbon allotrope. It is a single atomic layer of graphite, just one atom thick, measuring only 0.335 nanometers. Graphene was first isolated in 2004 by Andrei Geim and Konstantin Novoselov, using Scotch tape to peel layers from graphite, earning them the Nobel Prize in Physics in 2010. In graphene, carbon atoms are sp2 hybridized in a perfect honeycomb lattice with bond lengths of 142 picometers. Electrons move through graphene as if massless, like relativistic Dirac fermions, giving charge carrier mobilities exceeding 200,000 square centimeters per volt second, far beyond any other material. Graphene's extraordinary properties promise revolutionary applications. Graphene transistors can operate at terahertz frequencies. Graphene is ideal for flexible, transparent touchscreens, absorbing only 2.3% of visible light. In energy storage, graphene supercapacitors offer fast charging and high power density. Graphene sensors can detect single molecules. Graphene oxide membranes show promise for water filtration and desalination. In composites, tiny amounts of graphene dramatically improve strength and conductivity. The global graphene market is expected to reach billions of dollars. Let us compare these four allotropes. Diamond with sp3 hybridization forms a three-dimensional tetrahedral network, is the hardest known material, transparent, and electrically insulating. Graphite with sp2 forms two-dimensional layered sheets, is soft, opaque black, and electrically conductive along the planes. Fullerenes are zero-dimensional molecular cages, soluble and act as electron acceptors. Graphene is a two-dimensional atomic sheet with record-breaking strength and conductivity. Their densities reflect their structures. Diamond at 3.51 grams per cubic centimeter is densest, while graphite at 2.26 is less dense. Structure determines properties. Carbon nanotubes are cylindrical structures, graphene sheets rolled into seamless tubes. Discovered by Sumio Iijima in 1991, they have nanometer diameters, but can be centimeters long. Single-walled nanotubes have one graphene cylinder, multi-walled have multiple concentric cylinders. Armchair nanotubes are metallic, while zigzag and chiral ones are semiconducting. Their Young's modulus is around 1 terapascal and tensile strength up to 100 gigapascals. Applications include reinforced composites, conductive films, transistors, and sensors. Quiz question 1. What type of hybridization do carbon atoms exhibit in diamond? Option A, sp hybridization. Option B, sp2 hybridization. Option C, sp3 hybridization. Option D, sp3 dehybridization. Take a moment to think about your answer. Quiz question 2. Why is graphite an electrical conductor while diamond is an insulator? Option A, graphite is denser than diamond. Option B, graphite has delocalized pi electrons that can move freely along the layers. Option C, diamond has metallic bonding. Option D, graphite has sp3 hybridized carbon atoms. Consider the electronic structure of both materials. Quiz question 3. How many carbon atoms form the buckminsterfullerene C60 molecule? Option A, 50. Option B, 60. Option C, 70. Option D, 100. Think about the famous soccer ball-shaped molecule. Quiz question 4. How thick is a single layer of graphene? Option A, 0.335 nanometers, 1 atom thick. Option B, 1 nanometer. Option C, 10 nanometers. Option D, zero point 0.1 millimeter. Consider the definition of a two-dimensional material. Quiz question 5. Which carbon allotrope was first discovered in 1985 and earned its discoverers the Nobel Prize in Chemistry? Option A, graphene. Option B, diamond. Option C, Fullerenes C60. Option D, graphite. Think about the timeline of carbon allotrope discoveries. Problem 1. For each of the following carbon allotropes, determine the hybridization of carbon atoms, the bond angle, the dimensionality, and whether the material is electrically conductive. Diamond, graphite, fullerene C60, and graphene. Follow this step-by-step analysis. Problem 2. Explain why diamond is transparent and colorless, while graphite is opaque and black, despite both being pure carbon. Relate this to their electronic structures and band gaps. Follow along as we work through the explanation. Problem 3. The C60 molecule has 12 pentagonal faces and 20 hexagonal faces. Using Euler's formula for polyhedra, verify that this arrangement is consistent with a closed convex polyhedron containing 60 vertices. Calculate the number of edges and confirm Euler's theorem. Problem 4. Graphene's extraordinary electronic properties arise from its unique band structure. Explain the concept of Dirac cones in graphene. Understand why electrons behave as massless relativistic particles and what the resulting electron mobility is. Compare with silicon. Problem 5. Choose a carbon allotrope for 4 applications: a cutting tool for hard metals, a dry lubricant for spacecraft, an electron acceptor in a solar cell, a transparent conductive electrode for a flexible display. Follow the reasoning for each. Key concepts review. Diamond is sp3 hybridized, tetrahedral, hardest known insulator. Graphite is sp2, layered, conductive through pi electrons. Fullerenes are molecular cages, C60 with 60 atoms and pentagons and hexagons. Graphene is a single atomic layer with Dirac cones and ballistic transport. Remember Euler's formula for fullerenes and the Dirac dispersion for graphene. In conclusion, the story of carbon allotropes is fascinating. From diamond formed deep in the earth, to graphite in a pencil, to the fullerene soccer ball, to atom-thin graphene. Carbon's versatility comes from its 4 valence electrons that hybridize differently. Structure determines properties. By arranging the same atoms differently, we create materials that are hardest or softest, transparent or opaque, insulating or conductive. New carbon allotropes promise future technologies we can barely imagine.